Hiya, Nine. Right, okay, so we've looked at radioactive decay, and we know that some elements are unstable. Okay, so they have an unstable nucleus, and the way to make themselves more stable is by losing radiation. Okay, so we know that there are three different types of radiation. You've got alpha particles and beta particles, okay, and then you've got a wave of energy, which is gamma, okay. Now, we need to think about this whole process is spontaneous, it's random, we can't speed it up, we can't slow it down, okay, but each type of radioactive element has a particular rate at which it decays, okay. Now, we're going to model this idea in terms of, because we need to be able to come up with specific values for something called the half-life. Okay, now I'm going to show you two ways to do it. I'm going to show you the first one today, then you'll practice that. I'm going to show you a different way to work out those calculations tomorrow. Okay, so we've got this idea of half-life. So a half-life is the time it takes a radioactive isotope for half it to decay. Okay, so if you start here, I've got a set of atoms of this radioactive isotope. Okay, so it could be uranium, it could be carbon, it could be whatever isotope it is. So all of these blue dots are representing an atom of my radioisotope. Okay, so there's 16 of them in the first instance, and each one of them is unstable. Okay, now randomly, some of those will decay over a period of time, okay? And that period of time is called its half-life. So the time it takes for half of those radioisotopes to have lost radiation is called its half-life. So if you count on here now, I've gone down and I've only got 1, 2, 3, 4, 5, 6, 7, 8 blue dots, okay? So that time taken for it to go down by half is called its half-life. Now, after another half-life, another half will have been decayed. So I've gone from 16 down to half, which is 8. Okay, then I've gone from 8 down to 4 that are still radioactive. And then again, I've gone down by another half to just 2. So the blue ones are the ones that are still radioactive. So obviously the next one would be down to just 1 atom. Okay, now on average for each element, this half-life, so to go from 16 to 8 and then from 8 to 4 and then from 4 to 2, takes roughly the same amount of time, okay, on average. And that's its half-life. That's a given value of its half-life, okay. For some it will take place a little bit quicker, some it will be a little bit slower, but on average, okay, the half-life each time takes the same period of time, okay. Now, one way of showing that is on a graph. Now, I've got some examples of graphs here. I'm just going to use that to cover that over for the time being. So I've got some examples of graphs here. These are half-life graphs. Now, what this is showing you is the decay of your radioisotopes. Okay, so you've always got time along the bottom. Now you need to look at the unit that your time is in. It could be in seconds, it could be in minutes. Sorry, I'm just going to try and... There you go, that's a little bit better focus. It could be in years, it could be in thousands of years, it could be in hours or days, or what, all these different units of time, because some half-lives are very, very short, of just a few seconds. Some are very, very long, of thousands of years, okay. Now, we measure the radioactive count, okay, so how much radiation is being given out, in a unit called becquerels, okay. So the count is measured in becquerels. So this is a new word that you might come across, okay. So you can't predict it's going to when it's going to happen, but 1 becquerel is 1 decay per second, okay. Now on the graphs, what you do is you look at, the easiest way to do it is to look at how much radioactivity you've got to begin with. So in the first instance, the maximum radioactivity I've got here is 100, okay? And I want to find out its half-life. So I want to find out how long it's taken for it to drop by half. So half of 100 is 50. So basically I need to know how long it's taken for its drop from 100 to 50. So I'm going to draw my line across there and then down. And to go from 100, which was at 0, to 50 has taken 25 years. Okay, then to double check myself, I'm going to look at what the next half-life is. Okay, so I'm going to go, right, okay, well, how long did the next half-life take? The next half-life would be from 50 down to 25, which is half of 50. And I'm going to draw it across, okay, and then I'm going to draw it down. Now, at this point, I'm on 50 years, but it hasn't taken 50 years to drop by half, because remember, I was already at 25 years for my 50, and I've looked at how long it's taken to go from 50 to 25. So that has taken another 25. So in 50 years, there has been 2 half-lives, and my 100 has dropped by half twice. Okay, so I'll go through another example just so that I'm clear that you know what it is. So this time I've got time, but this time it's in seconds. So this is an isotope with a very small amount, a very short half-life. Again, I start at 100, so I'm going to go down to 50. Now on this scale, 50 isn't on here, so I'm going to have to estimate. I've got 40 and I've got 60, so 50 is going to be halfway in between. Okay, and then I'm going to go down, and I can see that from 100 to 50 has taken 10 years. So that's taken, not 10 years, 10 seconds, sorry. Okay, now if I wanted to check it again, I would go down and say, right, well, from 50 to 25, which is be another half, I'm going to go across again, right, and that would have taken another 10 years. So it's gone from 10, I keep saying years because the first one was in years. It's taken another 10 seconds. Okay, so I've gone through again 2 half-lives, and it's gone down half twice. Now if I wanted to say, right, okay, well, it's gone from 25 half again. Now that's going to be quite tricky because the scale on this isn't great. So, but what I would do is I would go across at 12.5, and I would find that that has taken another 10 years. So in my first, so I've gone from 100 down to 50, down to 25, down to 12.5. That is 1 half-life, that is 2 half-lives, that is 3 half-lives. So it's taken 10, 10 and 10 years. So all across there, 3 half-lives has taken 30 years. I don't think you spell lives like that, do you? That's lives. Anyway, okay. 2 more, just to make absolutely sure. So again, you've gone from 100 down to 50. You draw your line across to your line on the graph. You go down. So this time, again, it's in years. 1 half-life has taken 1 year. Going from 50 to 25. Oops, Daisy, I've completely missed that line. There we go. It's taken another year to drop by half. If I then go to half of 25, again, it's taken another year. If I went down again, you'd find it's taken another year. So in this case, a half-life of 1 year. Okay, I know it looks tricky once you've drawn out all those lines on, but you don't need to do all of those once you've got the hang of working out the half-life. Now in this case it's gone from 80, so I started off in 80. I've got a time of, my scale is in days. Okay, so I've gone from 80 to 40. I go across. I do exactly the same process each time. Okay, so that has been 2 days. To double check it, 40 down to 20 has taken another 2 days. So 2 half-lives has taken 4 days. Okay, now what you're going to do is I've given you a sheet on class charts to practice this idea. Okay, so to practice with the graphs, and then we're going to look at doing it in a calculation tomorrow. Where's my mouse?